All right. Welcome to the Game Engine stream. I think I counted 58 videos on my YouTube, so this is stream number 59. But yeah, welcome. Let me go ahead and see what we're. Let me really quick make sure I have all the stuff set up for my stream today. Audio's working. Got all my stuff ready. I think so. Okay. All right. So without further ado, let's go ahead and get into the updates. Well, before I start with any of the actual updates on stream, on the screen, you might notice I have a little guy walking around the bottom. So, yeah, I got the what are these called? Stream avatars. So, yeah, if anyone hops in, you should see your avatar pop in. I'm just trying stuff out. See how it goes, I guess. But yeah, I figured I'd address the elephant in the room. Anyways, let's check the actual updates. Having trouble uploading server to VPS. Yes, okay. So on my personal laptop, I'm trying to... Actually, let me see where it's at right now. Oh, it's AI. It's still building. I don't know. I guess I messed something up where it doesn't want to build the actual executable now. I don't know what I messed up on Linux, so... I've been trying to diagnose that like all day, even yesterday while I was streaming. I was trying to figure out what was going wrong with that. But yeah, as of right now, I don't really know. I'm trying a few things, but it takes a while for my Linux computer to compile anything. So I guess while I'm streaming, I'll be checking that periodically to see if I can get it to work. But yeah, hopefully I can get it uploaded onto the VPS soon, and then I can go from there. Otherwise, yeah, today we're going to work on more particles. I have some ideas on how I want to set up the particles. I was talking to it's a Discourager of Hesitancy. He does another stream that starts before mine about the particles system that I'm writing. And yeah, he said I was overcomplicating things. I think so. But I do want like a very specific method for modifying the particle types. I'm not going to write it like a full ECS, or I haven't even talked about that yet, but I have an idea on how I'm going to like set up various features for the particles, and I want to make it very what is the word, modular, I suppose, and I want to make sure that I maintain cache coherency. So I'm going to try it out today. I'm going to see how it works. Hopefully it's not too complicated. I've been looking at an article by the Flecs author, and he describes how he sets up his basic ECS with archetypes. And I think that might be the best use case for my particles, since the archetypes can place certain combinations of components into their own little like families, and then those families can kind of have their data like iterated through together. And that's like the main use case of the particle system, is that you use all of the components at once, you run through it, and that creates the final transformation that you see on the screen, right? And the nice thing about that too is I'll have separate vectors for each archetype, and then maybe I can set up like compute shaders, or I can set up like some SIMD with that, and they can kind of run on their own either threads, or from, again, if I'm setting up compute shaders, I can submit them as like specifically in the format that makes sense for that particular particle. This might all sound like a bit of rubbish right now. I'm gonna get into it as we get into the stream, but that's pretty much where I'm at today, or at the moment. So other than that, let's go ahead and check out the progress board and get on with it. So let's see. All right, so we're still working on the particle system. That hasn't changed. I'm not going to try and go like super deep into it. Like, I'm not going to add a UI and a whole bunch of stuff to it right now. I just want to get like a particle system working, and then I can go from there. because yeah, there's a lot I could add to it. Particle generators, lots of different lerp functions. Yeah, a lot of ways I can go about it. I can add a whole editor UI with a whole scene for like adding in particles and whatnot. Yeah, lots of things I can do. So I'm gonna try and refrain from going crazy with it. This is just supposed to be kind of like a fun side thing I'm doing real quick, in between adding text rendering, just so I can get my mind off of it. Because again, the other stream I was doing, I was going a little crazy with the trying to get everything to line up properly. So yeah, that's pretty much where I'm at with that. All right, let me make sure I'm not forgetting anything. Let's stream, update progress board, quick recap, previous stream. Yeah, so I'll show what we did previous stream really quickly, and then we can go ahead and get into the coding. So in the previous stream, yeah, let me just show, because we kind of left the engine in a very weird state with the particles being spawned and whatnot. It's kind of, yeah, I don't know. Let me check my little workflow thing. Oh yeah. So I can get rid of this. This was just some stuff I was keeping for a second. But yeah, get particles to render, add particles from scripts, and add lifetimes. Right. So basically, you can add a particle in the scripts and provide the lifetimes, and but no, the lifetimes don't actually work right now. That's what I want to get into next, but right now I want to add maybe like an ECS archetypes archetype-ish implementation. It does not need to be a full ECS for this. Really, I'm just like, I already know exactly which components are going to get combined, and there's no like adding new components in, like there's no UI to this. There's no like extra like any of that nonsense. This is all just going to be inside of the actual code, so it should be a lot simpler to implement. The main thing is just figuring out how to get it set up, and I'll kind of go over that in a second. But yeah, here we go. Looks like it opened up. Let's go ahead and run. So last time, basically, if I run this and open the application, it's going to start generating a bunch of particles. There we go. Yep. So that's where we were at last time. And it's going to keep going, and it just stays in the buffer because again, there's no lifetimes. So we just have a ton of particles that just keep getting rendered. So I think maybe the first thing is get rid of that code. Yeah. Or you know what, I'll leave it in for now. Yeah, so let's go ahead and look at the current code. Let's head over to the particle service. Move this stuff as well. Here we go. All right, init. Yeah, and that was a good point earlier with these time points. Yeah, because we do want to decrement all of their lifetimes. Or how do I say? The reason I have these high resolution clock time points is because I don't want to have to go through every particle in the buffer and decrement its delta time, right? It seems like a lot of extra work when you could just put a starting time point and then an ending time point. But this does use the system time, which is kind of not good because it doesn't reflect the actual in-game time, which is problematic, to say the least. Maybe I'll add an API for for getting the application time from the engine. And then these time points, I'm not going to go with chrono time points or whatever. I think I'm going to switch over to just some floats. Right. And then just go from there. So I think, yeah, we'll switch this over to a float. And then again, instead of using chrono times, we're gonna use how do I say? Because again, this does not need to be the most accurate thing ever. Got my phone. Let me turn off the notifications. Okay, here we go. All right. So yeah, switch that from chrono. We don't need chrono now. Let's head over to. Can I go to? I'm wondering if I can get to the other file from here. This is all the. I'm kind of getting like a million notifications from my like job thing. Hold on. It's going crazy. Okay. All right. Okay, I just want to get to the implementation file. Let's do this. Okay, here we are. All right, so now we shouldn't know what chrono is anymore. Okay, so I need an API for getting the current application time. Yeah, this is garbage now. So let's go to the engine, and we should be able to just grab the time from here, I believe. We have the M running, M minimized, M app start time. Okay. And then we're incrementing the. So this is just the start time. I don't know why it needs to be a double. It could just be a float, to be honest. Maybe a double is a good idea for this one, since it's the central one. Really quick, I'm gonna get some water. I'll be right back. Okay, I am back to the music tab. Yes, it did. Let me see. Just fixing up my music really quickly. All right, let's continue. All right, so can I get the time? Like, that would be nice. Okay, I think I do get the time in my stats page, I think. So let's do statistics. And I think I output the time somewhere in here. Utility time, get string from seconds, editor runtime. Yeah, this is the total editor runtime, that's cool. Okay, and I can get the total frame count. Okay, something along these lines actually. Yeah. So it looks like I am writing out the frame count. And then application runtime is a function where we get string from seconds. What is this? Yo. Okay, yeah, I don't know. But we're getting the time, glfw time minus get app start time. Okay. So that's interesting. And this one gets the update count. I think what I might do, because since we have a get update count, right? This is the total number of updates in the application. So if I run this, yeah, get active engine.get update count, right? Maybe I can get the current like application time by just multiplying the update count by the delta time, since it's a fixed step delta time, right? I don't know if I broke anything, but I think I did break something recently. But yeah, so this start and end time is different now. Let's go ahead and comment this out just for a moment. Do I do anything else similar? All right, let's go ahead and include the engine really quickly, and then I'll show you what I mean, what I'm doing. Engine, okay, core, engine. There we go. Then we push back, which is not in place back, but here's what it is. Okay, and again, for like the engine, the engine service, which is globally available, we'll get active engine, get app start time, get update count, right? Okay, and then this just returns the update count. I can only assume, right? Yeah. All right. And then maybe an easier thing I can do here is maybe we can return a float, and we'll say get application time. Okay, and that's kind of, okay, this is might be kind of confusing because this one is the app start time relative to the editor time, but this one is going to be the application time, like in the actual application. What I mean by that is it's the m update count times k underscore. I guess I don't define it here, do I? Okay, that's fine. I can make this occur internally, and you'll get that constant. Yeah, here it is. A underscore constant frame time step. There we go. So the application time is the update count times the constant frame time step. Right? This is a float. This is a UNT64T. So we're gonna, which is atomic. Ooh, okay, that's fine. Yeah, maybe I should not make that atomic. I'll see. Anyway, we're gonna convert this to a float and then multiply it over here. Get application time, huh? Okay, and now this is globally available, which is nice. Update app start time. So it gets in application time. Yeah, maybe I'll name it that. Okay, and then I'm gonna go back, and now it's going to be new particle at start time is equal to this, but not going to be updated. It's get in application time. We can float, which is fine, and then the end time, new particle dot end time is equal to start time plus lifetime. Easy as that. It's all floats, so it's nice and simple. Let's get rid of these. Okay, there we go. Maybe I'll put a comment here. Application time. And n times of set start and end times of particles lifetime or life cycle. I don't know. And then add particle to buffer. Create the new particle. All right, there we go. Easy as that. Let me check something really quick. Okay. All right, so that was just a quick change because basically what I just did is I changed my usage of time. So now my time is not based on the system clock. It's based on the amount of time that the application has been running, right? Which is good, because if the application happens to halt, as in the run loop happens to halt, right? The particle logic will halt along with the application instead of the time moving forward, and then the particles all get dropped, if that makes sense. So that's basically what that change just did. Let me run this. I want to confirm the update fix and everything, how that all looks and everything. That was a pretty easy addition. All right, then soon I can get into this ECS thing. Yeah, what I'm thinking is I'm gonna make a data structure for the ECS inside of my core section. So basically, over wherever I define all my like basic types. Somewhere in what am I doing? Engine. It's a lot of dependencies. Eek. Okay, editor UI. Okay, so back in core. So core is kind of my catch-all for all of like the basic fundamental types, right? And in data structures, I have just one data structure, right? But I could add some more data structures in here. So I think below this, I'll probably add like an archetype or all of the, data stuff associated with like a little ECS system, right? Like I could either put it here or I could put it in its own header file. I don't know. I'll see what makes more sense. Either one seems fine, to be honest. But as you can see in the core, I kind of just put like general structures that the rest of the engine uses. Also the profile, I don't know if that belongs here, but mouse codes, right, versus key codes. I think I have that in here. Basic logging is globally accessible. The engine is globally accessible. Directions, just cardinal directions that are just useful in general. Bit fields, we can use bit fields all around. When I start adding memory management, I'll probably put those structures in here as well. Base, of course, goes in here with all of its all of my macros, basic macros, and my refs, which I dislike more and more each day. Yeah, fixed string. Yeah, so basic types that are just used throughout the engine, right? UUIDs and stuff, wrap data, and whatnot. So yeah, I think I'll put the structure in here, and then after I put the structure of the ECS and everything in here, I'm gonna go back and just use it. And then that way I can just reuse it anywhere I need to have like a similar data structure, right? And I can just be using archetypes. I don't have to, I can set up the data structure once and then just use it wherever I want and get the same like benefits. So that'd be nice. And again, you might still be confused at what I mean by ECS with the particle system, like why, but I'll show you what I mean. If it ends up being too much, it's too much, but I think this will address a lot of the issues I'm already thinking of with this particle system as I make it more complicated. All right. So the thing I wanted to check here, I mean, it's good to compiled. That's a good sign. If I go to the panels and I go to stats, where's the stats? Stats. Why can I not find it? Wait, where's the statistics? I'm blind. Asset viewer? What? Or maybe, oh, it's in debug. Oh yeah, it's in debug, okay. Yeah, I was like, what? What happened to it? So you can see the application is not running, right? But the frame count is going up, right? Oh wait, the frame count's going up. That's interesting. The frame count is going up. Okay, and then application runtime goes up per the runtime. But I guess this frame count is like globally accessible. I think I use a very big number for this frame count. But anyways, you can see that this is just constantly adding and it's being used with each delta time, right? Actually, now that I think about it, I probably could just... No. Actually, no. I need the times to be relative to, like, seconds. So, no, I need to do the conversion. I was about to say, maybe I could just use the frame times directly instead of worrying about time, but... Maybe I could. Maybe I still could. Maybe I could just convert the seconds into frames using the delta time and then just toss that. Then just use the numbers. This would be a lot easier to calculate against. Yeah, I don't know. It's still doing this. So I guess so. But yeah, this is what I'm using. So yeah, it's good we can see it. Alright, so I think that's all the things I was dealing with just now. Yeah, so find data structure that works best for this use case. Yeah, so this is what I'm talking about with the ECS thing. I'm going to deal with this now. So, let me go to... Let's make another diagram. We're going to call this particles.dry.io. I don't know. Blank document, yep. We'll put this into Google Drive, pick a folder, and we'll put it into the stream section. It's an XML file. Interesting. Cool. All right. So here's my whole thing. Right, here's my whole proposition, if you will. I'm going to have multiple components, right? So this first component, and I'm going to put in here, is kind of like the bare bones of a particle, right? So the first thing is it needs a position. That is always a thing. We need a position. We need a size. Actually, yeah, that's kind of relative, isn't it? Position. Okay, yeah, we need a basic size. Yeah. Let me go see what else I have in here. Size and rotation. Yeah. So this just kind of describes the particle at its base form, right? And you can kind of call this, like maybe if I can give it a title, I don't know. A, right? Okay, let's copy all this and then paste it. Okay, so basically using this position, size, and rotation, we can draw a particle on the screen. We don't know what color it's gonna be, so by default, we'll probably just make it white or whatever. But now, if I want to add something more complex like physics, right? Okay, now if I'm doing a physics simulation, then I'm going to need a little bit more information, right? So for B, I'll say for physics, basic, right? For physics, we're going to need a velocity. We might want an acceleration. Depending on how we're treating this body, we might also want, if we're using box 2D in particular too, which is a bit overkill, we might want a box 2D, like ID as well. If we're just using box 2D along with like maybe some other box 2D preferences and whatnot. The velocity and the acceleration, you can probably leave, like this would be if you're writing your own little custom physics, which I might want to do, because if we're doing particles, we want to keep it as light as possible, right? So actually, you might even argue that this box 2D ID might even go into let's see, engine physics, right? Simple physics. There we go. And then this one, you might want a box 2D ID along with maybe the body type. I don't know. Whatever data, like, I think I have a bunch of stuff in my my rigid body for like my normal entities. There's a bunch of information in there describing like the physics body, and like you may need that, right? So this is if I'm using the physics from the engine physics, or I could just be using simple like my own custom written physics that might run a little bit faster because I don't need to add a bunch of overhead and in managing it amongst other things, right? Like I could just do this and not bother with collision or anything and just have it follow like a parabola or whatever simple equation I want it to follow, right? And then also like what if we wanted to do like a I don't know, like a basic color. So you might want to have like a vec4 for color, right? Versus maybe you want to do like a color that changes over time. And I'm not saying each of these has to be like its own component. You can probably like combine a few of these, and like it might make it a bit easier. Like having like a component just for like one vector is kind of busy. I'm not gonna lie. Like maybe this whole color thing could be like smashed into one thing, like you know, like a start color or like lerp color, right? So you'll have like a start color versus a vector for any color. Yeah, and then you would use these, right? When you want to provide a color, but when you don't want to provide a color, we just provide the basics, and then we'll just print like we'll just put out like a simple like white particle, whatever, right? And again, this is overkill. I could probably like push these two together and then just have like a start and end color for everything, and then yeah, that would be fine. You don't need these to be separate things. That's what it's one vec4, right? But you might see what I mean though. Like as this grows in complexity, we'll just have more and more different components, and then combinations of these components will yield like different functionality. Now, or like different output. So the basic like pipeline for like rendering a particle is going to be like you do the on update, which will like update like the information, right? So it'll do a bunch of like time step stuff to like move it along, and then like especially if you're doing like velocity rate acceleration, you want to like run your little physics calculation. Yeah, you want to run your little physics calculation, but in the basic case you might not want to do that, right? And in order to like choose which one you want to do, you're gonna have to like implement an throw in an if statement basically. So you're running an if statement for every single one, right? I'm thinking I could just have a series of function pointers, right? Where basically you can just define a particle that has like this, and this, right? And then this will be like archetype A. Archetype A. Right, and it just contains these three as like a contiguous buffer. Right, and then this series of like components, basically in the on update or in the on render in particular, all you're doing is just taking the basic position, size, and rotation, and all of the other like basic values, and you're just transforming those values to get like an output value, right? So we're going from here to here, if that makes sense. Right, and then each of these will have its own function associated with it, right? So you might have like physics calc, right? And then like here you might have a like lerp calculation for the color, right? And then of course with the basic ones you want to like, I don't know, some simple calculations, or like matrix calc, right? And then you run through all these like functions, and you end up with an output, right? And the output will be the final like location of the particle, how it looks, what shaders it uses. And the nice thing is if I have a series of particles, they can all kind of be contiguously packed into like a buffer with this exact size, right? And then you can just have like a series of them in a row, right? So you can do like a bunch of these packed together, and they all have the same buffer type, and they're all like cache coherent, right? So you just keep like stacking them together, right? And basically you're running the same function pointers through all of these, so maybe you can even take advantage of some like SIMD processing, because you're doing the exact same process to all of these. So maybe you can take a big chunk of them at one time, and then just apply the same transformations to them like flatly, if that makes sense, right? Especially if it's just a simple like float times float type of deal with these, or like, you know what I mean? Yeah, because they would all be applying the same like time or time step deal with it. So yeah, that's my idea. And then you could have like a bunch of archetypes for all of the different combinations of these. And there's no like front end to this. Basically, we're just getting a big buffer of this archetype contiguously. And then if we have another one that has a different combination of these things, that separate archetype can go down into a different buffer. And that different buffer will require a different series of actions to occur with that buffer. But again, you can kind of inline all that stuff to happen together at once, right? So my idea first is to kind of make a like base data structure that just allows for this whole process to work. And then once I get this basic data structure set up, I will apply it to the particles. So I'll have a bunch of like individual structs for each of these things. I'll add a bunch of function pointers that are associated with the actual actions that need to take place when you either run the on update or on render, right? And then from there, it'll just run. And the other nice thing too, is since these are all doing similar actions, if I eventually want to work on like compute shaders, or I want to add some parallelization with just basic, add some parallelization with just some basic multi-threading, I can work on these buffers separately. Like, so I'll have one archetype, and then I'll have like archetype B down here, and then that one can run in parallel, right? Because most of its stuff should be, how do I say? Separate, yeah. The only limitation I'm already kind of thinking of though is that objects that have like the same item like this flatly, I might have to be aware of the ones that all have a particular component, but that's a little extra. Yeah, I may have to think about that. For the most part though, particles should be fairly like, they shouldn't mess with each other too much, right? But yeah, that's basically the idea from archetypes right now. I'm gonna run through Sander Merton. He has some blog posts about his basic implementation of his like Flecs ECS, right? So I'm just gonna follow through this and kind of make my own little implementation through these two blog posts. And then once I get this basic implementation down, I'm probably not going to name things the way he names it. I'm probably going to change it around because it's just archetypes. I'm not going to try and make a whole ECS, like proper ECS out of this. Some of the functionality of this is not needed in my particle system. So my main thing is I just want to have nice buffers of contiguous memory that all do the same thing. And I can like pick and choose at like which particles have which components and kind of mix and match them, and then everything still remains fairly performant. And you don't usually typically need to like pick out individual particles, right? I mean, I could add a system for that, maybe adding like an ID to each particle or something, but that could be added as like a component, maybe. But typically I shouldn't really need to do that. The particles for the most part should just be their own buffers. They work on their own little section of the world. And yeah. This may seem like I'm kind of overcomplicating things, but I'm just trying to get it set up in a way where I can add more features later on, and it's not like a huge hassle, because the route that I was going down by just adding a whole bunch of features to this basic particle struct is I'm going to have like a giant buffer of a whole bunch of random features and a bunch of if statements being ran for every single particle every single time. And I have a lot of ideas of how I want to set up particles, add like custom shaders, add you know, a bunch of features, right? I don't want just basic particles, right? So I'm thinking, okay, how do I make sure I don't end up with a giant Uber class that's going to be like tanking performance, because I want to have a lot of particles on the screen. So yeah, let me turn on this music really quick. Okay, anyways, so yeah, I guess that was my long belabored introduction to what I'm doing. Took like 40 minutes. It's just fun. Alright, so okay. I guess I'll put this in data structures and I'll start working on this ECS system. Quote unquote ECS. So I'm gonna follow this just verbatim for a little bit and then just go from there. Data describes how to replace more efficient ones. This is the first series and posts. I'm just gonna read reading for a little bit. I'll take about 2 or 3. I'm gonna change the music too. It's a bit of a lot. There we go. First, I'll talk about 2 to 3 fundamental points: entities and types. Entities are unique things in your game, often presenting a unique integer value. Combine the entity and type concept to build the first data structure. So you have a using type, this, and then, okay, so let's copy this over. You know what, I'm gonna give it its own file. Call this R type .h. Okay. Namespace Cardano. This will be in the global namespace. It's fine, because it's just a basic data structure. All right, and then we're gonna do a class, and then, well, let's not worry about that yet. We'll just add this in. He's using std vector and then std on order map. I probably will change this soon. We'll see. So hash include vector. I'm just gonna copy it verbatim for now, just so I don't start adding too much complexity on my own. Order. Okay, entity ID and component ID. Okay. Is this the first one? This is the first one. Okay. Using type is a vector of component ID, and then an order map is an entity ID. Okay, so I'm going to assume that an entity ID using entity ID is equal to, and I'm definitely going to change this name later. I don't really want to call it an entity. It's going to be a uint64t. And then let's go ahead and just make sure that's not broken. estd int. Okay, and then a component ID, I'm just going to assume it's the same thing until I'm proven wrong. uint64_t. Okay, and then this one is just a floating thing here, so I don't particularly love that. think for now, I'm going to make a class for an archetype. And then in the private section, I'm going to go ahead and toss this in here. And then I'll go ahead and start doing an entity index. Entity index. Component ID. Just name it that for now. I'm going to put a public section up here. Okay, this will be an object, so I will provide a constructor and destructor to this. Might be a good idea. Let's head over to the engine and grab this. This private. It's interesting. I don't know if that's a good choice, but archetype. Archetype. Okay. And I'll say internal that. All right. Defines. Archetype supporting defines for the archetype. Like that. An archetype. Okay, there we go. It's more my style. Yeah, that should be fine. All right, let's go check this. Okay, so entities are unique things in your game, yeah. So in my case, an entity would be a particle. Describes the component data type in ECS. Describes the component data types a specific entity has, which can be represented as a vector of component identifiers. For example, a first-person shooter could have a player entity that has component position, health, yep. We can combine the entity and type concepts to build the first data structure of an ECS framework. Yeah. Let's quickly query for a given entity ID, which components it has. Uses a data structure very similar to the one described here for this exact purpose. Okay. So has component, we just provide the ID along with the component ID. And then we just loop through the vector. Or well, we grab the type from the unordered map. And then we loop through its types until we find it, and then we return. Yeah, it's pretty simple. I'll go ahead and copy this over. I don't know if I'm really going to need this. Actually, I'm pretty sure I'm not going to, but I'll just grab it for completion's sake, I guess. And I will add an implementation file for this. Let me comment this out for a sec. Oh, no. Sorry. And yeah, let's add an implementation file. Archetypes.cp. I did add primal once, right? I think, yeah, the thing on does that for me. Which include agpch.h. I gotta rethink that pch file as well. Namespace chrono. Okay, and then we'll go ahead and add some stuff here. So let's this, and then as components, the entity ID and a component ID. Okay, entity vector reference, yeah, I can agree with that. Type is a vector of. And we're going to do the component ID map. This is an auto, which I'm not a huge fan of, I'm going to be honest. Just a component ID, which is a 64-bit integer, which is fine to toss in here in this case. Stuff being descriptive. I wonder if I should call this archetype, because this is kind of the archetype, I'm gonna be honest. Yeah, you know what? I'm gonna call this an archetype. Okay, I don't love that, so let's go ahead and move that over here. Return false, okay, yeah. Let's go ahead and take this bit out. Also, this is a const function, so let's go ahead and hopefully, yeah, because it's gonna modify it. That's the one thing. I always forget what they say is the alternative to this. I could do at, but that's kind of... Yeah, because I remember if you do this, it's not there. It actually inserts that object, which is so weird. Okay, I'll take const off for now, even though this really should just be a const thing. Actually, yeah. Let me just ask ChatGPT. Maybe he knows. Maybe I'll call it archetype context, but I tend to use context in a very specific way in this engine, so yeah, I don't know. Maybe I just did this. Okay, how can I access the map without inserting in this function? But then inserting it into the function, what are you talking about? Check if it exists, if it... What about in C plus 20? The thing is, like, doesn't ats have like some overhead? But then again, doesn't the other one have overhead as well? I don't know. Okay, we're just gonna do at. We're gonna be a little dangerous here. Oh yeah, no, that's my bad. Okay, fine, I'll drop the cost thing. Yeah, because it is grabbing a reference which it could modify. Yeah, okay, sure. Alright, let's keep reading. Alright, let's take a look at the type of entity. The entity is a 64-bit ID, yep. The component is a bit trickier. It needs to be a unique value for each data type we add to Flecs. So Flecs knows what you want to write, yeah. After these two operations, we want our entity index to contain a vector for players. Data type we add to contain a vector for player that contains position health. Because we can't store types, doesn't have a notion of type ID, we need to come up with our representation. Assign unique integers to each data type, which is exactly what Flecs does, yeah. So 2 type of player can be stored like this. Whenever you do because this definition of ID is exactly the same as that of entity ID. Okay, so each component ID is a unique number, right? But I would assume you might want to do like a bit mask for it. The only thing is that does limit the number of options you have. Pretty fast, to be honest. Oh, I'm back. Okay. The component ID is assigned to a data type whenever you do ECS component or components. It is not just useless reductionism. It lets us do a lot of cool things that help many of Flecs features. For now, this gives us a nice and concise way to describe our ECS design. Type, yep, so we got that. Or in plain text, an entity is represented by a unique integer. A type is a vector of entity component IDs. The entity index stores entities and their type. We can use this design to describe our previous example. So all of our entities and components. Note that since component IDs is the same as entity ID, we'll just use the ID from now on. Contents of an entity index looks like this. Okay, so for 10 we have nothing, 20 we have nothing, for 30 we have 10 and 20. Okay. This was fine. Yeah, it's a vector of component IDs, right? Okay. And you just need to make sure that each ID is unique. And he's not doing a bit mask or anything, which is interesting. I might end up doing a bit mask, but maybe there's a reason he didn't do that. I know they do that in the ent library. Anyways, with these IDs, the content of the entity ID looks like this. Now, yeah, so we have a map of 10 for the particular entity, and then you have no components in that particular one. Not just player 30 shows up in this index, but so that entities for position and health. Okay, we can store both entities and components in a single consistent data structure. It's not the whole story though. An entity that represents a component has a special component. The entities that represent a component have a special component that describes the data type it represents. In Flecs, this is the ECS component. Okay. Let's update our definition to include this. Entity ID ECS component ID is equal to 1. The position ID is 10. Health ID is 20, and player ID is 30. As entities that represent a component have a special component the data type represents. Describes what an entity that represents a component. ECS component ID. Since one is a component itself, it has itself in its type. During the bootstrap, when you call ECS init or create your world, our entity index is becoming a bit unreadable though. This is not just a problem in the example, but also when writing applications you want to inspect which component an entity has instead of a list of integers and entity names. For this reason, Flecs introduces the ECS ID component. Okay, the same entity index names instead of numbers looks like this. Yeah. So it's like now it's so you have an ECS ID and an ECS component. So this describes the component. And then a player. Oh, okay. So we have entities that just describe a particular component, and then we have players which are just an actual entity, right? And it has an ECS ID. What's up with the ECS ID again? So far we described how this design lets us store entities and which components they have. One of the biggest implications of the design is that we can add entities to entities. Since a type is a vector of entity IDs, it doesn't matter for Flecs whether an application adds a component or a regular entity. Oh, I got you. Yeah, so you can have like sub-hierarchies. That's why they have this. So you can add a component. So it kind of gets like a tree structure, I guess, that you can do. Yeah, I don't care about that, I'm gonna be honest. I really don't. Let's construct hierarchies or more simply graphs, but let's stick with hierarchies for now. Yeah, so parent child. Prove this though. The OR operator adds the child of bit to my platoon, which could write this code. It's common in games. Yeah, I don't care about this, I'm gonna be honest. I mean, it's cool, but that is widely used in games. The C Flecs is the ability to create reusable assets and prefabs. Okay. Get color. Yeah, no, I'm gonna get over to this one. I think this is the one that I actually care about. Archetypes and vectorization. Because the rest of those were just kind of like extra features that are nice in a general ECS, but in my situation, I don't care. I don't need hierarchies, I just need a flat list of components. Arrays, and then let's see how this goes. You have a column, okay, and then this is all the elements and buffer data. I want to see how he keeps this cache coherent. That's kind of my main thing for this. Yeah, and adding components is just moving things around, but in my case, I don't need to worry about this. This would have a lot, I'm assuming a little bit of like processing requirements if you're adding components to an existing entity, because you have to actually move that entity out, right, of its current archetype. But in my particle system, I won't have that issue because there really shouldn't be a reason to be moving particles from one archetype to the other. Once you put a particle in an archetype, it just stays there until its lifetime dies. Keep track of entities in the entity index. We can inspect the components of an entity by looking at its archetype. Yeah. We can check if an entity has a component with the component index. Archetypes of a set of components. We can quickly remove. Yeah, that's cool. Now let me read this really quick. A list of component IDs. Yeah. A column is a component vector. Yeah, I'll probably rename that. Edges to other archetypes, so struct archetype edge, add, remove. Assuming that's some. Oh, okay, so this is like the edges of it, which you can like expand or contract it, I guess, if necessary. Types, type used to store each unique component list only once. Type used to store, so struct archetype ID. Okay. There's the type of it, which I guess is different. That's interesting. I'm assuming the archetype ID is generated from the type, because the type is a vector of unique numbers, and I'm assuming the archetype ID is some unique hash ID of it that can easily be queried. And then the vector of components, it's the vector of columns. That's interesting. And then we have an unordered map of component ID to archetype edge. That's interesting. Component ID. Archetype edge. That I don't understand. Find the archetype by its list of component IDs. Type to archetype. Okay, that's cool. So we get this archetype from the type. Isn't the type a vector though? I guess the vector of integers is hashable by default. Yeah, I think I would change that implementation though. Instead of, I mean, I get that the type is specified by a vector of component IDs which are unique, right? But I think a faster way of doing that maybe is just define like a specific maximum for the integer, and then we can just do a bit mask. And then that bit mask, you can like assign each one to like a separate flag in the bit mask, and then you can just do a quick like check like that, right? Instead of this. I'm assuming he does it like this for a reason, because he has other ways that he like moves stuff around and whatnot. But I might be able to get away with it, because again, I'm not making ECS. I'm just trying to get cache coherency and things in the same buffers. Find the archetype for an entity. So you provide an entity ID and you get the archetype reference. Okay, so this is a separate owner map that links to this actual buffer, right? This can be kind of scary because this is a reference to this, which can get broken. So you got to keep these, consistent. But yeah, you can find the archetype for a particular entity, which is cool. And then, but also, I don't think I'm gonna need that too much with my particle system. I mean, it's good that I have this though. That might be useful in another archetype system. But in the particle system, I'm not really worried about that. record in component index with component column for archetype. Size t for the column. Record in component index with used to look up components in archetype. Used to look up components in archetype. Archetype map is unordered map of archetype ID to archetype record. And archetype record is just the size of the column. Component ID to archetype map. Okay. Interesting. Yeah, let me take a quick peruse of this. I'm not going to write the code out directly, but let me just see what this does. The ABC. Unfortunately, storing all data in perfectly contiguous arrays is not trivial. Yeah, it's not. To see why, let's look at a simple example first. Imagine we have an application with 3 entities that all have component A. We store this in a single array. We can use the array index for entity ID so that A of 2 gives us the value of A for entity 2. Now imagine that 2 of these entities also have component B. For this, we need to add an array for B, but here we run into a problem. We could create an array with the same size A like this. It still allows us to use entity as an index. So we have an array of 3 and only 2 entities, so we can't guarantee that arrays can take. Yeah, this means that we cannot vectorize our code. This is not good. So let's try store as many B's as we need by creating an array with just 2 vectors. But yeah, trying to align it like this is going to have a lot of wasted memory. Even though A and B are stored in contiguous arrays, the entity IDs don't match up. And this is kind of what ent does, but it doesn't waste as much memory because I think it uses pagination or something like that. Or I don't know the exact implementation, but they kind of get away with. Well, they actually just store all the A's together and all the B's together, and then they use like bit masks to like grab a whole entity at once. But the idea of ent is that you would just loop through a single component. That's like the main use case, right? Or you would combine multiple, but and you would still probably run through the vector linearly as long as everything's organized, but that's kind of hard to put together. I don't know how ent does that whole thing. It's a lot of management. But I'm choosing archetypes for this case because it makes the most sense for the particle system. This is a, so yeah, okay, so even though they're contiguous, their entities don't match up. Yep. Problem solves, inversely nuts. Yeah. So what if we stop trying to create a single array per component, but instead create an array per component per type? Imagine we have 2 entities with A, 2 entities with A B, and 2 entities with AC. We could store them like this. Yeah. So we'll have 3 separate vectors, which is a little more processing. But at least all of these will have the same memory together. And since A and B are together in memory, you don't have to reference 2 separate vectors to get like a position data and a physics data. They're pushed together in one section, right? Kind of like how you would just, if you wanted to do this manually, you would just define a bunch of permutations of structs, and then you would just define every permutation that's possible if you wanted to. Like that's basically what this is, but like programmatically. So now we have, yeah, we just have a buffer of A's and a buffer of AB's, and they're all the same exact size, which is really nice. We now have 3 separate arrays for A, which introduces a little bit of overhead, yeah. That we fixed our previous problem. All the arrays are contiguous, yep. Okay. All right, to make this work, we need to group all entities with the same components together. As it turns out, we already have something that keeps track of unique component combinations, the archetype from the previous blog. And again, an archetype is an archetype ID and a type. I can extend this type so that it can also store components. So I say using column. Okay, so now with each of these archetypes, we are also storing a vector of type T. So that I'm going to go ahead and put here. So instead of having this type as just a vector of component IDs, and also this is now going to be archetype context. Okay, and now we're going to do a struct archetype. And then he said that he wants to have a type. I'm probably going to argue with this and say maybe a bit mask might be better, at least for my implementation. But yeah, we'll see, I guess. All right. Archetype. So we have a type. And type. And then we have a say like what do you say? So the archetype ID, which I'm assuming is also a uint64 until I'm proven wrong. So archetype ID and ID. Probably spelled that wrong. I don't know. Archetype ID. Yeah, I think once I know how he's keeping all of these vectors contiguous, I'm gonna just do my own thing. So to make this work, we need to group all entities with the same components together. Yep, I'm gonna send this so that we have all those. Okay, so we're storing the vector components. We're storing this vector of components directly in the archetype. And this usually does not know the archetype T beforehand. This is usually an ECS. This is why ECS usually needs to apply a technique called type erasure. Allows components to be stored without knowing what type it is, which yeah, that's probably what I'm going to do as well. But I might be able to get away with templating since I already know what all the types are from the beginning. But yeah, it would be nice to have a like void pointer buffer. Yeah, so we have it's a void pointer. That's interesting. I'm probably just gonna do like a uint8 underscore t buffer. Elements, so the size of an individual element and the count. Yeah, I can agree with that. Now that we can store and iterate components in a way that is cache efficient, we can actually find the value of a component. Getting a component. To find a component value for an entity, we need to extend the entity index in data structure described. Just to recap what that looks like. Ordered map. It's for an entity ID to an archetype reference. So the entity ID references an archetype, it doesn't actually store it. Lets us find the archetype for an entity. It does not tell us at which index in the component array we can find its value. We can fix this by adding this index or row to the payload of the entity index. So we have a record, and then an entity ID to a record. With this in place, we can now get the value for a specific component. Wait, what? I got lost there. So find the archetype for an entity icon that does not tell us which index in the component array we can find its values. We can fix this by adding this index or row to the payload of an entity index. So we provide another unordered map of entity ID to record, and then that record will reference the archetype and then a size t to index, indicate where to find it, I guess. And then we get an unordered map of entity ID to record. That's cool, I guess. I'll get the value of our specific components. Okay. So get components. So we grab the record, and then we grab the archetype from the record. Right? And then what was the other thing? We get entity ID to an archetype, so we can get the archetype, and then we also get the record. Where's R? What is this R? Where'd you get this from? Does it mean record? Yeah, so that's what he means. Okay, then first check if the archetype has component. Yeah, and then for the individual components, we do a bunch of stuff. We're starting to get somewhere, but this code has a linear search to get the component value for an entity. Yeah, I mean, the linear search I could deal with, like, for a particular archetype, you could just store the locations for everything in like a component type. Yeah, like this. The set though, is that necessary? It's a set of archetype ID. So to do this, we require extending the component index. We use this in our previous step to test if an archetype has a component, but if instead tell us in which column the component is stored, we can do this by simply adding a payload to the archetype size. Yeah, I mean, yeah, still not really the problem, adding components. Okay, here we go. Here's where, like, I'm trying to figure out what we're doing. So adding components, if a component is added to an entity, its archetype changes. This means that to make this work, we need to do two things. Find the archetype that has the component we want to add in addition to the entity already has, insert a new row into the destination, remove the overlapping components over in the destination archetype, and then move it from the current archetype. Yeah, so I don't need to do all this because I'm probably not going to be adding and removing components from entity, but I do want to see how he handles this. Say we have entity with archetype position and velocity. Add to it. Do is find or create archetype. To copy the position and velocity, then we need to remove the row from the position. Yeah, we need to copy the data over, and then we need to remove the row. Yeah, it's just a bunch of like data manipulation. Finding archetype, a big factor in how fast you can find the next archetype. In the previous post, we used a data structure that used the type vector as a key in the map. It's not very fast. Consider the steps. Yeah, be fast enough for operations we want to do in the main loop of the game. Don't change components often. This may be fine. On the fly, yeah. So we'll move between the same archetypes many times. This means, yeah, entities will move between the same archetypes many times. This means we need many archetype searches that have the same parameters. If there is one entity that has, yeah, I don't care about this given that we already know. That's all I used to know originally. Okay, I'm gonna take a break really quick. I'll be right back. I think I just need to think for a little bit. So yeah, BRB. Okay. Okay. I just had an idea on how to get the functionality I want, and I just remembered it from when I was reading about the Ents, the way they keep their vectors densely packed. So I'm not going to worry about any more of this archetype stuff. I mean, I am going to use it, definitely, but I'm going to do it my own way. Because, yeah, I think he's trying to address a lot of things that I'm not really worried about. Alright, so we have archetype context, right? The first thing is we need a buffer, right? So we'll do another struct, and we'll do an arc. Archetype buffer. Okay, and the archetype buffer is going to be a very interesting thing. So the first thing is going to be a uint underscore t. Pointer is going to be a data buffer. Pointer, right? We're going to say data. That's the first thing. So we need to actually access the data payload. It's going to be would it be heap allocated? Yeah, I think it would have to be heap allocated. Well, I guess it wouldn't have to necessarily be heap allocated. You could stack allocate with a certain size, but for now I'm going to keep it heap allocated to keep my life simple, and then I'll add more restrictions later, I guess. So then we're going to do I could also do like an SD array or ST vector of rates. That is a possibility. Because, yeah, I need to figure out how big of a buffer I want. And maybe I don't want to have to manage that data myself at the moment. Because, yeah, there's three ways I can do this. I can either manually define like a limit for what's the max size of a particular archetype buffer. Right, that is always a possibility. I could also how do I say? Put a vector here and let it auto size itself. Maybe I can put like a dot reserve, so I can reserve a certain buffer size immediately, and then just use that buffer, and then it can resize as needed, right? I definitely could do that. Or I could just manage the buffer myself using like a data pointer with a size, and then I have to do all the heap allocations myself with it, but it still might be dynamically resizable. So I'm going to go with the easier option right now, which is just a SD vector of bytes. And then later, if I want to like optimize this, maybe make it more stack allocated, I can go ahead and do that. I could do uint 8t, or I could do a car. I think uint 8t is a bit more descriptive, right? Okay. And then we're going to need two indices. So, actually, no, we don't need two indices. We just need one index. So, I say size t. Ending index terminal index, I guess. And then we also want the size of size t of m archetype size. Maybe I'll just say type size. In this archetype, I think what I'm going to do is I'm going to include the flags. So include Cardano core bit flag, bit field. That's what I meant. We'll be using this fairly heavily. All right, and okay, well, this is just going to be like a buffer, right? It's not actually going to be an array of type T, right? I'm not really worried about that. But the accessor functions probably will use templating, so it will do a bit of like type redefining to get out the correct buffer type. But yeah, we'll get to that. M type size, M terminal index. So I'm going to need this to dynamically resize the buffer and keep it contiguous. And then this is an archetype. They're going to have an archetype buffer. Archetype buffer. Buffer. The arc buffer. Buffer. Okay, that'll be stack allocated, so that's fine. And then we have the type and then the archetype ID. Okay, so there's a few things I'm gonna need with this archetype. The first thing is I need to have like a vector of indices. Maybe I'll change this later, like a smarter thing or something. And I'll say M component indices. Right. So that way, when I'm accessing this particular archetype, I know how to grab out the individual components. Yeah. Okay, and then this being an unordered map, I kind of don't care about the entity ID, I'm not gonna lie. We're not really going to be accessing each entity individually. For the most part, we're just going to be looping through a bunch of buffers, right? So the main first thing, yeah, I'm going to get rid of this entity ID. Component ID? That's a good question. I don't know. I don't know if I need to deal with the component ID. Let me check the bit field. How do I set this up? Because I'm assuming it's going to be a bit field. A bit field for the data type. Okay. So component index. Let's see. Archetype ID. So instead of having a vector of component IDs, I'm just going to use a bit field. field. And for the bit field, I guess I need to define how big I want the thing to be. I guess I'll go with a should I go with a UN64? I don't know. UN64_T. So this will give me 64 different components I can add. Is that overkill? Maybe. Okay. Yeah, I might call this archetype ID actually. And a component ID will be something inside of this UN64, so oh, actually, yeah, it should actually be a UN64, as I think about it. Because if we want to use it as a bit mask, we need to be able to specify the 0th bit, 1st bit, 2nd bit, all the way into the 63rd bit, which the 63rd bit will be a massive number that can only be contained in a 64-bit integer. So that means this has to be a 64-bit number, right? Yeah, and that's it. So component ID and the archetype ID. Easy as that. Using the bit field, we can access the actual underlying number and use that as a unique identifier. Because since we're using a bit field, the actual integer will be different for all the permutations. Well, not permutations, for all the combinations. Okay, so we don't need double E, we can just do this, right? Okay, so we need something to describe the size of an actual component somewhere. I don't know where I should store it though. Probably here, right? So we'll, I don't even, okay, should this be an unordered map actually? Honestly, it could just be a vector for now. A vector of archetypes. Because again, for now, we're just going to be accessing it linearly, so I don't need to worry about having a map or anything. Well, it might be nice to access a particular archetype, huh? Well, I'll add that later if it's really necessary. Oops. Archetypes. And then we also want, and this one is going to be interesting. This one says it's going to be a map, so unordered map. Or unordered set, let's see. No, map. Yeah, set. Yeah, map. Okay. And then this is going to be a unit _T. Does this just convert into a data type? Yeah, because it only contains this data type, so maybe I can, I don't know. Is it hashable? Oh yeah, maybe I can. ID. Oh yeah, because it's just a number at the end of the day. The archetype ID can lead to struct component description. Spec. I don't know if spec is the right name. Info? Okay, component info, I guess. No, because the indices will be different per archetype. Now I think about it. Let me see. STD vector of size T component sizes. There we go. This one can probably be an array, although indices. You know what? Let me change to 32. And a component ID would be 32. Like, do I anticipate there being more than 32 components for this? I mean, there could be, but and that'll reduce the complexity of this a lot. I want to switch this to an array. That'd be nice. Sizes. I'll say a UN 16 or 15. I don't know if I'm actually saving any memory though. Memory's for the key. $216. $216. Yeah. Oh, just realized my dude was offset. Wait, what? Hold on. Just fixing my OBS really quick. All right. So I'll say note this system can only hold a maximum of 16 different components. I'll just make that an arbitrary. I mean, I could modify that, but yeah, I'll leave that as the arbitrary requirement for this. It's a vector of u and 16 t's. Okay. As component. Okay, so I'm not worried about this anymore. Let's go here and delete this. Yeah, I'm wondering if I want to keep this as a vector. I'm gonna do an array. Yeah, I'm gonna do an array. Yeah, so it'll be a uint 16 underscore t with a maximum size of 16. Because yeah, that's the maximum number of components that we can have. And I might make it so that like you can specify the size in the actual like definition of this. And that way, if you specify the size, you can kind of expand it to the number of components that you might need, right? And then maybe I can reduce this down to even like 8 if that's required. But yeah, that makes this more stack allocated, which I like better since we're going to be accessing this a lot. And 16 times 16, I mean, that's decent. It's a decent size, but it's nothing too crazy. And it's only being defined once for this system. Or for this particular archetype, and then, you know, it's not for every single particle. So, I'll trade a little memory, fine. Alright, so now we have an order map of archetype ID. So what is this for? So I have a vector of archetypes. We have an archetype ID to what? Okay, well I gotta remember what I'm trying to do here. So we have the buffer. Let me think. I'm gonna loop through all that data. Then for each function, we're gonna grab out the relevant data. Yeah, this should work, I think. Yeah. Okay, well, we'll just throw this for now. I'll figure out what's actually necessary while I'm writing it. So the first thing is we need to add things to the context, right? So should I switch this vector into an unordered map just so I can make adding particles easier? That is a pretty common thing. So yeah, probably, yeah. So unordered map. I'm gonna do archetype ID to archetype and archetypes. Right. Okay. Now we're gonna say we'll just say void. And now add I'm really trying to not say entity. Like I'm really trying not to say entity. I guess. We just need to provide an archetype ID. Which is really easy because it's just a number. Objects. To archetype. Create object. Entity. Alright, sure, whatever. So this create entity function, the first thing it should do, it has the archetype ID by default, so if m underscore archetypes dot contains ID does not contain ID, add archetype to buffer. It'll say m archetype dot creates a new archetype. So, and then insert archetype. So the end goal of this is just to say m archetype type dot inserts or assign. I think it's one better. Then we're gonna do ID and then archetype, new archetype. So archetype, new archetype. new archetype dot MID is equal to ID. New archetype dot arc buffer. We need to, well, once you create it, it's an array, so yeah, it's a vector, so it'll be fine. The index should start at 0 though. And then the size should be I mean, we don't need to, like, if we have this as a buffer, we actually don't need the size now I think about it. We just need the terminal index. The size information is in the vector. So this will be allocated correctly. It's already like a 0 buffer, that's fine. The only thing is we need to fill this information. Yeah, since this is stack allocated, this will be fine. This will be initialized, but it needs to actually have the correct information. So here is where we're going to need to add some information. I think I'm going to add maybe elements info. So for the component info, we need sizes. We just need the size actually. Using components actually, we don't even need to do that. We'll just do this. SD unordered map. And then we're going to do component ID, component ID, and then we're going to do a size T. Component sizes. Then this can get initialized when we add a component. So we'll need to like add a component. Void add component. And then we need to provide it a component ID. And of course it's kind of interesting exposing this directly to the end user. So I probably will add a little bit of functionality on top of this, but at its basics, you want to do the ID as well as the size. That's really all you need, honestly. Then the size, the component size. And there you go. And then this will do some checks to make sure that we don't already have this particular component. And then we can kind of go from there, I guess. But the main thing about this is just you're going to do M component sizes, insert, or assign, ID, and then component size. Now, of course, here we want to do add check to ensure it is a new component. So, I mean, one thing I could do also is just instead of providing this component ID directly, I could just compute the next component ID and then just return that back, and then you can just use that however you want, I guess. Yeah, I might actually do that. There's new components. Okay, so now you can add a component, and then you can create an entity. So the create entity will its archetype will be basically gets all components and what is this again? Component sizes. The ID has all this information, but it's kind of spread amongst the ID itself, so maybe std array of uint 16 underscore t. Maybe uint, yeah, 16 underscore t. Or I could be more specific, components ID 16. Component IDs. There we go. So we can figure out what index each one's at. Or actually, I mean, we can probably get the index from just these two. Because as long as it's ordered in the correct manner, then yeah, if you go to ID1 and you compute the size, then ID2 compute the size. Oh, but then what if you just want one particular component out of here? No, actually, I'll cache the memory, it's fine. We'll compute this now, so later accessing this will be really easy. Yeah, I may even want... Let's see. Let me think. Yeah, because in this case, I would have to loop through each component in this array to figure out where each one stands. No, wait, actually I need an owner map. Unordered. Not super in love with this, but whatever. An ordered map of, what is it? The component ID to its index. Component index. And then we can get rid of this. Okay. So the idea would be if you wanted to access a particular component, you'd run into the unordered map, you'd provide the component ID that you're looking for, and you would get the index of these two arrays that you needed, right? And then say if the component is at 2, right, you would just access index 2 of this array, and then figure out what the actual oh, wait a second. Component buffer index. Buffer loc. Comp buffer loc. Component buffer location. And then size. Yeah. So you would grab the component. Well, if we're using an unordered map, I might as well just put all the data. Oh, but if it's going to be unordered, that might be a problem, huh? Yeah, my main thing is if I want to access a particular component, I want it to be as fast as possible. Yeah, maybe this stuff. Maybe this stuff should be with the actual component data. Yeah, this should be computed when the component is generated, maybe? Oh, no, wait, but the archetype is... No, this is where the series of components comes together. I see. Okay, I'm gonna take a quick break. I'm gonna think about this again. BRB. Okay, let me go back and see something really quick, because this is an interesting problem. I want to go back and see how he was doing this. Or like accessing a particular object. An unordered map of entity ID to archetype. To archetype. Okay. Archetype.type.count. Type, and you provide the number. Wait, what is type? Again, I'll come back down to the bottom and see. Type is just a vector of IDs. Okay, interesting. Type is just a vector. Type is just a vector of IDs. Yeah, interesting. Good to slam. You alright? How are we able to access that so easily there, though? Okay, do you wanna? Okay. Give me a sec. You wanna come up here? There's not really much here for you. Okay. Actually, I'm gonna use the restroom really quick. I'll be right back. All right. Let's see. Just trying to get somewhere, but this code. Wait. So how are you doing that? Entity index. Entity component. First, check if archetype has component. So component index. Archetype.count. For component ID, return for arc.count. If type ID is equal to components, return columns record row. Okay. Okay, interesting. Regarding the component index structure described here is the recap. Stats. Archetype map. Component index. If components archetype.count component ID is equal to 0. Wait, I'm kind of lost in that. To find a component. So what it is, which requires extending component index data structure described. Here's a recap of what it looks like. Archetype set component index. Use this in our previous example to test if an archetype has a component. Struct archetype record size t column. Archetype map. Is an unordered. Oh wait, so this is an unordered map of archetype ID to archetype record. Size t of column. Archetype.count. Archetype.id. Unordered map of component ID to archetype set. If instead of as just telling if an archetype has a component, in which column the component is stored. Oh, okay. So you have a, oh, my brain was working. You have an unordered map of component ID to archetype map, and the archetype map tells you, wait, we have an unordered map to an unordered map? What? Sure. Sure, yeah, that's interesting. To the actual location, to the size. And I'm already aware of the component size, I'm assuming, so then we can just get it. Okay, wait, so if I go back here, well, I guess we just need its buffer location. We don't even need the size. Because I'm assuming if we're accessing a buffer, yeah, we just do this. Which means we could just store an unordered map. Of the component ID to unit 16. We're not doing that to yeah, to the location. Well, actually, in component buffer location, right? And that's all we would need. The only thing now is that we might want to go straight through this archetype. So how will we do that with this? Its archetype is a series of bits in the bit field, and if we want to test, we'd have to test every single one to check which ones are contained. Which is kind of annoying. This is assuming we have the component ID. So if we have the component ID, then we can easily check if it exists with this ID, which is easy. But yeah, the other thing is I just want to make sure that I'm able to linearly go through this buffer in the correct order, right? So I might want to just a map instead of an unordered map, which is a bit slower. It's kind of annoying. Because yeah, I believe it's a tree that we're accessing in that case. Okay, so we may need that vector. I use the numbers. Is there anything I can do with that? Okay, fine. So these two structures will provide what I need. Yeah, these two will provide what I need. So basically, if you want to access one particular component, then you can just use this unordered map, right? And then this will just grab you that location. You can, inside this buffer, right? And you can use that location in the buffer to cast into the component type that you need. So it's like a quick grab, right? If you need to loop through this buffer, then you would use this component ID. And then this component ID, you can use in conjunction with this unordered map. To get, how do I say? To get each individual buffer location. I could combine these two into, how do I say? Into one map. Like just one straight map, and then it will, yeah, it will sort it by the component ID, which would be nice. And then you can still, but all of the operations will be O log n to access the data. What is the time for looping through? Yeah, what is the time and complexity of accessing a map in C++, like a regular map? Yeah, I mean, I always know that unknown map has better quick checks of the thing, but yeah, this combo, I could just go through each component and then like just query this map really quick and get the integer. But I would prefer something a bit more clever, I feel like, because a lot of map hits is going to be occurring all the time. Mm-hmm. 3, 6. I wonder if it's easy to get the individual flags. Yeah, get raw bit field is flag sets. Enable all flags. They're all flags, yeah. Follow the flag. And then we can easily check or compare different fields or these, yeah. I think there's an easy way to loop through all the flags in a bit field, but that's not really what it's made for. Yeah. Okay. Okay. So I think that's good. Hmm. Oh my, there really is a cat crying. Get out, just let out, dude. You're alright. You'll be alright. Hmm. Okay, kitty. It's gonna be alright. It's gonna be okay. Meow. Mm. Yeah, okay. Mm. Okay, okay. Let's move on from this. My brain's getting a little all over the place with this. I don't know. Should I continue doing this, adding this archetype thing? This might be too much. No, I think it's worth it actually, yeah. Because yeah, if you have a particular archetype, you can just loop through the vector, right? And as you're looping through the vector, you can grab each object. Yeah, you can grab each object. Yeah. Okay. So you can loop through the vector and get all the component IDs, and then you can loop through those IDs and get each actual data buffer. Yeah, okay. Okay, no, that's fine. That's fine. Yeah, yeah. Okay. I was staring at that for a long time because I was kind of going back and forth in my head about this unordered map. But all right, let's move on. Let's move on. So add component, right? Just inserts that component along with its size, yeah. And then create entity. Maybe we'll add a internal private void create archetype. Archetype ID. So for the archetype ID, we can loop through the M component sizes, which I think is the only way that we store components, really. It's an unordered map, though, isn't it? It is, yeah. Okay. Create an archetype. Archetype ID, huh? Okay. Maybe I'll leave the archetype ID in here. Or component sizes. Auto. Component ID, and then component size. It's gonna do an SD set. Component ID, there we go. IDs. IDs. Alright. And we're just gonna sort it like this. So comp IDs dot inserts components ID. And now we're going to do a for comp IDs to components ID. Okay, now this is where we're going to start creating the archetype. So we'll do this, yeah. Okay. And then the new archetype. There we go. We'll insert the archetype. This is having an issue because it's not a member. We don't know. Wait. SD set ID less is not a class member. What are you talking about? It's just a unit 16. Also, yeah, it's just bothering me to use the lowercase. I like it like this better. Okay. Oh, wait. Wait, doesn't this include the KGPCH? Also, this is Cardano core/archetypes. Still having an issue though. Wait, in my KGPCH, don't I include set? I do. Okay, so that's not a problem. What if I did a uint 16? I'm just what, do I need a 32-bit? Oh. It's ID. Components IDs. Yeah, I don't know why I did M underscore either. That's weird. Okay, there we go. I was like, what is going on? New archetype dot M components inserts, or I guess just push back and place back. ID. There we go. And also new archetype.m buffer location dot insert or assign to do ID, and then we're also going to provide the buffer location. So uint16_t buffer size buffer location is 0. Buffer location, and then buffer location plus equals m_component sizes dot, maybe I can just do this ID. Yeah, because that gets the size. So then we'll just add up the size and then just keep going. Put the component IDs in ascending order. And then store component locations and ordered list, or ordered list of components and their locations. Buffer indices. And then we just insert the archetype. Okay. Is that it for the archetype? Let me see. New archetype. Arc buffer. Yeah, the buffer is just a SD vector, so we're fine. Okay. That should do that. So instead of doing this, we're just going to do add a new archetype. It's going to be create archetype with the ID. We'll do all this nonsense. All right. Now insert entity into archetype. Okay, so in this case, we're just going to how do I say? Return a component ID. And then we're just going to provide the component size. Component ID. And then we're just going to provide it with the size. Okay. And then we're going to say, we're going to keep another variable here. It's going to be a uint16_t. Final terminal component index is 0. Okay, so terminal component plus. And then we'll do a gonna say const expert inline uint 16 underscore t. A maximum components is 16. Or the index would be 15, I guess. Index, maximum component index is 15. Yeah, I'll do another one. Const expert inline uint 16 is for t, k invalid components index is we'll find max dependencies here. For size t, that'd be weird. Unit 16 is for t. K invalid component index. What is wrong? Guys, close this. We'll do an early check. If terminal is greater than or equal to a maximum component index, kg warn attempt to add a component to an archetype. However, maximum components reached. Okay, and then we're going to return a invalid component index. And then yeah, you would never have a component index that's all ones. That is just an invalid, that is a valid flag, but it's an invalid component index. Okay. Ensure a new component can be added. If it can be added, then we're just going to do it's bit 0. Or bits of terminal. Components ID, new ID is this. And this is just a, like, you provide like the bit location you want and it gives you the actual number back. Like the actual integer value back. and that is the component ID. Then we increment this. Create new component ID. Create new component ID. And then new ID. And of course, this is what we're going to be comparing against. Okay. Okay, so that should add a component along with its size. And then it'll return back an ID, and you can just look at the ID and be, okay, is that valid or not? Then create entity. This will, you provide an archetype ID, which would be a combination of components. Check something really quick. Wait, what? Let me block my thing really quick. Oh, okay, never mind. I thought I was having an issue or something. Never mind. It's in the wrong place for some reason. There we go. Alright, let's put it back. Create new component ID. Okay. Insert entity into archetype. Okay, so here is going to be interesting. Basically, we're just going to push it back, right? I mean, Okay. Okay. So what I'm gonna do is check if. Okay, we're gonna need the size of this particular archetype, right? Oh, let me store that with the archetype actually. And 16 MGT size. Arc size. Okay, we need to store this somewhere. Might as well be here and say what new archetype dot archetype size is equal to buffer location. There we go. It's easy. First, ensure buffer can be expanded is big enough for new entity. If I just thought about it. I'm not gonna do a vector. I'm going to do terminal index, that size t buffer size 0. And then we're just gonna handle this data ourselves. So we're gonna do a uint. We'll do a void pointer. And data buffer. Or actually, I have something for this. I should include chrono or buffer. Let's see. Let's check out this abstraction of a buffer I have. Okay, buffer defaults, buffers defaults, buffer allocates. Copy. And then constructor. Let's do a constructor. So arc type. Let's put this here. It's getting a little bit more complicated, but that's what it is. It's because we need to start managing this buffer ourselves, so we're going to say make sure I don't make a memory leak with these buffers. Buffer, and then that way I don't need to keep a size anymore because this buffer maintains a size and a data pointer. That's essentially all it is. Yeah, just that. What does the constructor for this do? It does nothing. Okay. Set data to byte, allocate, copy. Do I want to manage this thing? I don't know. You know what? Never mind. Let's just do STD vector. 8 square T. So this will maintain size. Insert entity into archetype. Insert buffer is big enough for new entity. Okay. So if we'll get the archetype. So archetypes dot at ID this will give us an archetype reference. Archetype reference archetype. Okay. Insert buffer is big enough, so if archetype dot n arc buffer dot n data buffer dot size plus arc dot m arc size wait. archetype size. Size underscore t greater than archetype dot arc buffer dot capacity then archetype dot arc buffer dots and buffer dots. Is there a quick like double in size? Resize to capacity times 2. You do the GCC thing, I guess. Oh, that's bright. Let's see. Reserve. Okay, so let's just make sure that the buffer is bigger. Or is sized correctly. And then we insert the entity into the archetype. And the size is actually in bytes. It's the actual, it's a vector of bytes, so these are actually in the same terms already. Greater than, and then we're basically just resizing the capacity. Yeah, so this just gets this minus this. Insert entity into archetype. Yep. So we're going to do archetype dot arc buffer dot data buffer. Insert entity into archetype. It's archetype. Let's see. Data buffer dot data plus archetype dot okay, you know what? Let's do size t buffer size equal to this. Buffer size t buffer capacity equal to this. I'm using it so much. Or actually, an even better thing maybe I can do the entity vector of u int 8 underscore t. We're going to say reference buffer is equal to this. Okay, and this will cut down on all this because I'll just do buffer.size, buffer.capacity, buffer.reserve, and then buffer.capacity. Buffer.data, there we go. Way better. Times 2. Guess I messed that up. Alright. Archetype plus m underscore arc buffer dot m terminal index. So we're going to do a mem copy. Pretty dangerous. So this is the destination. The source is oh, we're gonna have to actually loop through all of the things. Okay. So we'll get it. Okay, how long have I been streaming? I think it's been like a few hours, right? Yeah, almost 4 hours. Okay, yeah, I think I'm getting kind of tired. My brain's not really working right now, so yeah, I'll go ahead and stop right now. Let's just see if this builds. I don't think we use this anywhere, so it should be fine. And yeah, I think I'll call it from there. Oh, what's wrong? Int from narrowing conversion. Oh, int to that, yeah, so 1650. It's fine. Yeah, narrowing will just loop if it provide the wrong number. What is this? Size T to oh yeah. Numbers 14. There we go. I won't fix that error though. What's wrong? Should taking one argument. Hash. Something about a hash. These are always annoying. Okay, I must have inserted something wrong. Yeah, this takes 2 values. Yeah, well, push back. Or is it the map? I'm pretty sure it's the map. Yeah, maybe I should do this. Here, let's just make sure this is the right thing. No, it's not one of these. Okay. Maybe it's this one. I've been doing all three of these wrong. Oh wow, wait, what? Is it this one? Wait, which one's wrong? Wait, what? Or am I, okay, I'm gonna be missing one more. I'm gonna find the culprit. Pushback? No. What? There's no way it's that, right? What? Okay, let's comment all this out. Comment all this out. And comments. I'll say return 0. And comment all this out. And then I'm gonna put them back one by one and then see if I can find the one with the issue. Oh no, yeah, that build, okay. Debug, build, cancel, okay. Put this back. Yep, one of these, okay. Type reserve. Okay, I'm just gonna comment all this out for now and I'm too tired to figure this out right now. I don't know, my brain's not working. So yeah, I think I'll call it for here. I'll figure this out tomorrow. Trying to see. Okay. Just checking something really quick. Okay. So what did I change in the particle service? Oh, this is a pretty important change. Change usage, change time point usage in particle service. That's not H. From chrono library into floats. Floats that use the engine's time object. And then engine.h add to get application time from engine.h. And then start creating archetype structure. Start creating archetype data structure. In archetypes, that's p/h. Okay, add archetypes. Oops. And small time changes. Okay, let's commit that. All right, and yeah, I think I'll call it for today. So let me make sure I got everything. Prescription code, yep, I didn't change any game code. Park sports exactly the same. I should be on tomorrow for the stream. So yeah, I don't think anyone came into the stream today, so yeah. If you're watching this on YouTube, thanks for coming, watching the video. I appreciate you. Hope you have a good day or night. And yeah, I guess that's about it. All right, later.